Good afternoon. Welcome to the RSES Manufacturer Webinar Series. I am Lori Casales, RSES Journal Publisher and Editor. I'd like to welcome everyone to today's session on Designing for Natural Refrigerants, which is being presented by John Prahl. Before we get started, I'd like to thank Embraco for sponsoring today's webinar. Their generous support is how we keep webinars free for members, and we value their shared commitment to educating HVAC professionals. John's presentation will last approximately 45 minutes. Afterward, there will be a Q&A session. You can submit any questions you have throughout John's presentation using the GoToWebinar dialog box, which is on the right-hand side of your screen. I'll field the questions and ask them aloud to John. Today's presentation is being recorded and will be available online for viewing at your convenience as soon as possible. Now I'd like to introduce our presenter for the afternoon, John Prahl.
Hi, thank you for joining our Natural Refrigerant series. Today, we're going to discuss how to adjust your system for handling hydrocarbon refrigerants. Much of the material you're going to learn today is probably stuff you're already familiar with, but let's hope that some of this is a refresh for you and will help you remember what you learned back in your early days of engineering. And maybe there'll be some new ideas that you can utilize with the development of your latest products using some of these refrigerants. What we're going to focus on today is meeting this 150 gram limit using R290 and R600a. First of all, the reason we're having this discussion is because of pending DOE energy standards coming out in 2017. These standards are extremely aggressive, some of the most aggressive in the world. And part of the solution to meeting some of these energy requirements is to use natural refrigerants like R600a and R290, which naturally give you better energy efficiency than R134a and R404a, which they are replacing. On top of that, there's a potential EPA ban on using R404a, R507, some of the R407 series, and R134a, in new and retrofit vending machines and retail food refrigerations in 2016. Right now, that date doesn't look likely to stick. However, we need to move forward as if it will until we hear further information from the EPA. Another thing to mention is that using these hydrocarbon refrigerants in refrigerated equipment is safe. We're talking 150 grams of refrigerant, or about 5.3 ounces for R290 in commercial applications. And in some household applications, only 57 grams of refrigerant is allowed, which is about 2.5 ounces. This is equivalent to about 2 or 3 cigarette lighters. With this 150 gram limit for R290 and R600a, most light commercial applications can be covered using these refrigerants. When you need a charge larger than 5.3 ounces, you may have to look into using dual circuits to achieve this charge limitation. And this is what we're going to focus on, is adjustments to the system to help hit these limits. Just to keep you informed, there currently is an IEC group that's been put together that are looking at finding a way to get approvals to increase this charge limit to 300 to 500 grams. This would cover almost the entire plug-in range using a single circuit solution. This IEC group is expecting to take about 2 years to get approvals in Europe, and typically we see that the UL and EPA would follow these IEC regulations by about 2 or so years later. Again, this is all pending studies, nothing's in stone, but it's something that we're working towards. Right off the bat, switching from R404A to R290 gives you a 45 to 50% reduction in refrigerant charge. Going from R134A to R600a gives you a 35 to 40% reduction in charge, and 134A to R290 is a 45 to 50% reduction. This is before you've even taken any changes to the system itself. Naturally, these refrigerants have more capacity to them per volume than the other refrigerants that they would be replacing. So let's go to a basic cycle overview, just as a reminder. In the first step, the compressor is going to compress the vapor into a high pressure vapor. This vapor is then sent to our condenser, where it is condensed into a liquid, and then it enters our expansion device, which could be a cap tube or a TXV. This hot, high pressure liquid is reduced in pressure and will flash into a small mixture of a low pressure vapor and a low temperature liquid. This liquid will then enter the evaporator, where it proceeds to boil away into a low pressure, low temperature liquid, where it will return back to the compressor and repeat the cycle. These are the four main components that we're going to focus on talking about today. Starting with evaporators. With evaporator sizing, the first place to start would be right around where your original 134A or R404A system was. First thing we need to understand is what is the overall TD of the system, understand our superheats, and then pay attention to our airflow and fin design on the evaporator. When designing our evaporator, we need to account for two TDs. These temperature differences can be driven by the efficiency of your evaporator. First TD to look at is the cabinet temperature versus your product temperature. Typically, this is going to be 8 to 15 degrees of a delta between your actual food temperature and the temperature in the cabinet. Also, we need to look at the temperature difference between the evaporator and the ambient as well. Also, this will be 8 to 15 degrees. The larger your TD, the lower cost of your evaporator is going to be, because you have less material, because you're going to have a smaller evaporator. The unfortunate side effect of this is that you have a less efficient system. The greater the TD, the more work you're going to have for the compressor. Now, a small TD will give you a more efficient system because you have more material and lower TDs. The side effect of this is higher cost and increased volume. What you want to make sure is find a balancing point where you're able to get a good charge out of the system and get good efficiency. If you have extra efficiency to play with, you may want to look at reducing your evaporator size. If you don't, you'll need to increase your evaporator size to decrease that TD. Also, we need to pay attention to our superheats. We want to see at least 5 to 6 degrees of superheat coming in the evaporator. Too much superheat generally is an indicator that your evaporator is too large and that your boil is ending too soon. Or you could have a restriction in the system that is increasing the pressure drop in the evaporator greater than you need. If you have too little superheat, that could be an indicator that your evaporator is too small and that you have too little pressure drop in the system. You may want to consider increasing the length of your capillary tube to increase your pressure drop in the system. If you like to design with a flooded evaporator, keep in mind that that will increase your charge because you have more liquid in the system than you would normally have. One thing to consider is airflow is very critical to the behavior of your evaporator. You want to make sure you have as much air moving across the evaporator and that it's not spilling into other areas of the cabinet and bypassing your evaporator. If you have the capability, try and do some CFD modeling to ensure that the airflow is flowing in the correct direction, or try and use some tape to monitor how the air is flowing through the cabinet. The greater your airflow, it gives you the ability to lower the TD and give you a smaller evaporator, which has a reduced internal volume, and you get better heat transfer. If you have the option of using increased air velocity, such as a higher speed fan or a larger fan blade, try and use it. However, the consequence of this is more energy consumption and an increase in noise. With fin design, this is critical to your heat transfer. Fins are the most important point in removing heat from your evaporator. They give you the best heat exchange. The trouble is if your fins are too tight, you run the risk of excess ice building up on the evaporator, and you have to increase the number of defrost cycles you have to remove this ice, particularly in low temperature applications. As you increase the spacing, the effectiveness of the evaporator is reduced as well. So finding a balance is going to be critical. There is some free software called EvapCond, which you can download and use to help analyze the design of your evaporator and determine its effectiveness. One thing to consider too is with your evaporator, pay attention to how the fins are designed. If you have cut fins or wavy fins, you get a better heat transfer because you're creating turbulence with the air. The greater the turbulence of the air going through the evaporator, the better heat exchange you will see with the system. One thing we've noticed in our own testing is that rifled tubing in the evaporator has very little impact on the overall behavior of the system. It's an added cost that you may not see much benefit from. And always remember to respect the compressor's envelope and be sure that your evaporator is operating within the evaporator temperature ranges that the compressor is designed for. Next topic is condensers. As with the evaporator, the best starting point is the heat exchanger would be the same size as your existing R134a and R404a. Again, we're going to take a look at the TDs of the system, understand the subcooling of the system, and look at airflow and tubing. With the condenser, there's only two TDs that you need to pay attention to. The condenser temperature versus your ambient temperature. As with the evaporator, the larger your TD, the lower the cost of your evaporator will be, and you get a reduced volume. However, you have a less efficient system, so you're going to have a higher condensing pressure than you would have with a smaller TD. The advantages of a small TD is that you have a much more efficient system. However, because you will now have a larger heat exchanger, you're going to have added material cost and increased volume. The impact on the condenser will be greater than that in your evaporator because the system is flooded with a high-pressure, dense gas and a liquid at the end of the tubing. So there's more volume in that, more volume of gas and vapor, or liquid and gas in that system, in that portion of the system than there is in the evaporator. You also want to make sure that you have good subcooling leaving the condenser. Typically, we want to see between 5 and 8 degrees of subcooling leaving this condenser. Too much subcooling is an indicator that the condenser is too large, or you have a constriction in your cap tube that is resulting in flooding in the condenser. A good indicator if you have a constriction in the cap tube is very low evap pressure, very high superheat, and very high subcooling. Too little subcooling is an indicator that your condenser is too small. The risk with this is that you could have bubbles entering your cap tube, causing poor performance in the cap tube. So you want to make sure you have a good quality of liquid leaving your condenser. And you'll see better results out of your cap tube behavior with this. And as I mentioned, high subcooling can be a result of a restricted cap tube. As with the evaporator, airflow is again key to performance. The more air you're able to move over your condenser, the better the performance of your system. Again, consider a higher velocity airflow with a larger fan or a faster fan speed if possible. Take a look at CFD modeling if you have the capability, as with the evaporator. Moving on to fins. Your fin spacing needs to be considerate of the environment you're going to be in. For example, if you're in a relatively clean environment, 12 fins per inch may work well for you. However, if you're in an area with pet hair or lots of dust, you may want to look at 8 fins per inch and lower. This will help avoid any clogging of the condenser and keep the condensing pressure as low as possible. Other performance options to consider are cut fins, wave fins, and again, anything that would help create air turbulence through the condenser to increase the heat transfer throughout the coil. And also pay attention to your airside pressure drop through it as well. And as with the evaporator, again, pay attention to the compressor's envelope. You don't want to raise the condensing pressure outside the envelope that the compressor can withstand. This would shorten the life of the compressor. Some things to help with the condenser size. If you're finding that you're not able to achieve the charge with a 3/8 inch tubing, consider using 5/16 inch tubing as well. Also, microchannel condensers are a good way to reduce charge dramatically. Again, there is going to be a cost impact with going to microchannel condensers. But if you really need to meet the charge, it's a good way of getting there. Another condensing method to consider is water-cooled condensing. Water-cooled condensing would give you a very low charge because the volume of refrigerant that would be in the condenser is very small, because water to refrigerant has a very high rate of heat exchange. Ideally, with water-cooled condensing, you have a constant condensing temperature, so you have better control of the operating conditions of the system and get better performance out of the system. Also, you have no fan noise because a fan is not required to do water-cooled condensing. However, if you do have a fan-cooled compressor, some airflow does need to be maintained across the compressor shell. You don't have to run the risk of having a blocked fan failure, and you can get lower condensing pressure if you use cooler water. You can reduce the condensing pressure, and with that you get more capacity out of a smaller displacement compressor than you would get using air-cooled condensing. Some of the disadvantages is that you do need a water loop, whether you're using a chiller or just tapping off of the city lines. These chillers cost money and add a significant cost to the overall project, but if an existing water source is there, it's a great thing to use. Also, flat plate heat exchangers are more expensive than your traditional air-cooled condenser would be. Now we're going to move on to our expansion device. Expansion devices are cap tubes and TXVs. The advantage of cap tubes is that they're very inexpensive, they're easy to get a charge balance from, and you can use them as a suction to liquid heat exchanger to get additional superheat and additional subcooling into the compressor and out of your condenser. Also, they do not require a high start torque compressor, and you can use a lower start torque. Some disadvantage to them is that they're much harder to size than a TXV. They can clog quite easily, and under varying load conditions, superheat is going to fluctuate. They're also not as flexible as a TXV in that you can't use them for a multi-temperature type application, a product from a low temperature product to a medium temperature product. TXVs have the advantage of giving you better control over your system. They're more flexible for the type of application you want to use them in, and they're easy to apply. You set the superheat you want, and it will maintain that superheat. The disadvantage to them is that they cost more than cap and typically they require a high start torque compressor unless you have a type with system to equalize in between compressor starts. There's three major ways of applying cap tubes on the system, and each one has an system efficiency, but also an impact on cost. One of the most effective ways of running a cap tube is to run them inside your suction line. This would give you good superheat return to the compressor and good liquid subcooling out of your condenser. The other option is to braze the line along your suction line, and it has a similar impact, though not quite as good. And finally, the capillary tube could be wrapped around the suction line and brazed on that way, or just hung loose. It's not as effective, but it does provide this a little bit of additional superheat and subcooling as compared to not having that in the system. All of this results in an improvement of efficiency and a reduction in mass flow. And this reduction in mass flow will enable you to lower the charge of your system. An ancillary item in all of this is the receiver versus accumulator. Receivers are typically used with TXVs and are located in the high side of the system. As a result, these items will store liquid as the ambient conditions change. In low ambient conditions, you will have excess liquid in the system that will pool in this receiver. In warmer days, when the system needs more mass flow, you'll find that the receiver empties out of liquid. The net result is that you could see an increase in charge in the system because of the addition of this component. Accumulators are typically used with cap tubes and located on the low side of the system. These help protect the compressor from liquid return when you have a varying ambient condition or a varying load condition, which could result in liquid leaving the evaporator and heading to the compressor. This is a problem with cap tubes since they are not able to maintain superheat. The nice thing about accumulators is because they only have vapor refrigerant in them, there's a minimal impact in charge as compared to the receiver. Other items to consider. Always try and minimize the copper runs in your system. The more line runs you have in the system, it gives you more places for the refrigerant charge to hang out, and this could increase your refrigerant charge. When you apply your filter dryer, try to use the smallest filter dryer you can find. This helps also reduce charge because these can store refrigerant. Another thing to consider is use hot gas defrost on these types of systems. It helps remove a potential spark point from the system. However, you need to make sure that your compressor is going to be able to handle the high mass flows of these type of situations when you go into hot gas defrost, and that the compressor can handle any risk of liquid return from doing this. And finally, larger systems may require dual circuiting. Typically, we find when you hit over 3/4 horsepower systems, whether it be a low temperature application or a medium temperature application, this is about the breaking point where achieving these capacities using a single compressor becomes a limiting factor with that 150 grams. And just to summarize, when you start trying to adjust your system to meet hydrocarbons, the best place to start is just to swap out the compressor and adjust the cap tube. From there, find your charge balance and see where you are. If you're under 150 grams, you're good to go. If you find that you're over 150 grams, then start playing with the components. The condenser is probably the easiest component to target to try and reduce refrigerant volume. And then after that, taking a look at the evaporator is a good place to go. With that, I'm going to hand it back to Lori, and we'll open it up for questions. Thanks again for your time, and I appreciate you joining this presentation.
All right, John, back on. If anybody out there has any questions, go ahead and use the questions tab on the right side. I'm going to keep it on your screen, John, so in case you have to refer back to a slide.
Okay, sounds good.
Okay, we do have one question. It says, I saw something about cap tube sizing versus R404A. Reduced by 15%?
Yes, that's the good starting place to go, is to take your existing R404A and reduce by about 15% in cap tube length.
We have another question. Can you tell me about the pressures of these refrigerants?
Yeah, R600 is a very low pressure gas. It's a little bit lower than R134A. I'm drawing from memory here. At 20 degrees, it's around 3 psi, and it pulls into a vacuum right around 8 degrees Fahrenheit. And then at 110 degrees, well, actually 130 degrees Fahrenheit, it's around 100 psi. So a pretty low pressure gas. So if you have a leak in the evaporator, it's actually going to pull outside air into the system. R290 is a higher pressure than R134A, but lower than R404A. What's nice about that is it's those lower pressures are actually easier on the compressor and gives you a lower oil temperature and a lower discharge temperature, which prolongs the life of the compressor. So R290 at minus 20 is going to be around 10 psi. At plus 20, it's going to be around 40 psi. And at 130, it will be around 250 psi.
Okay. John, do you have a website that you wanted to mention as well on natural refrigerants?
Naturalrefrigerants.info is where we have most of our information on natural refrigerants. And also, if you have questions, please feel free to reach out to me.
Okay. Thank you. Here's another question. In running cap tube inside suction line, how much subcooling is possible?
Well, that's dependent upon what your evaporator temperature is and what superheat you're going to be getting. It's going to be very system dependent. Typically, I would expect you to be able to get at least 5 to 10 degrees of additional subcooling. But again, if you have a specific application, please reach out to me and we can talk through that.
Okay, just to clarify for everyone on the line, if I do not get to your questions, I will send copies to John so he can respond accordingly. I have another question. What percent of refrigerant is in the condenser versus the evaporator?
Oh, the evaporator has a very, very small amount compared to the condenser. Well over somewhere between 70% more. Well, assuming that you had 100% of the refrigerant in the evaporator and the condenser, it's going to be at least 60 to 70% in the condenser compared to the evaporator. Again, that depends on how flooded your evaporator is and where your condensing is in the coil. Evaporators typically do not hold a whole lot of refrigerant.
Okay. I have another question. It says, what are the rules and laws of using 150 grams or less of flammable refrigerants in Canada? That might be too specific for you, but you might know.
Right now, the rules are, again, everything is subject to a local code. So at the end of the day, any local jurisdiction may override, but the rules are typically the same as the U.S., where in an occupied space, you can go up to 150 grams without having to do too much. There may be a few exceptions here and there. I don't have the Canadian rules memorized, unfortunately, but CSA typically follows UL.
Okay. I believe I'm getting a serial number in this question, so I'm going to read it slow. In the FFU 130UAX, how much refrigerant will the oil absorb?
Typically, you can expect oil, regardless of the compressor, to absorb around 6 to 10% of your total charge, maybe a little bit more. So if you have 150 grams, you can expect about 15 grams, maybe up to 20 grams to be absorbed in the oil.
Okay, and someone else asked what oils are used.
There's R290 is good with alkybenzene oils, mineral oils, and POE oils. Most of the oils that we're using would be POE. Some compressors are using alkybenzene. And then typically you're going to see a 22 centistoke or a 32 centistoke viscosity with the oil. And some of the really high efficiency models could be down to 10, and we have some R600 models that are down around 5 centistoke.
Okay. Another question with a number, I hope you understand. Are the small copper dryers lower volume than the EK032?
I don't have the volume of that EK02 memorized. Just a rough guess, I would assume so.
Okay. And let's see. What is the efficiency comparison of R134a versus an R290 system with 150 gram limitation?
Yeah, the 150 gram limitation wouldn't impact efficiency, but the just a drop-in replacement, when you do a 134A to R290, you should see around a 20 to 30% improvement right off the bat. And with R404A to R290, you would see around a 15%, and that's without making any adjustments to the system. That's just swapping out the compressors and going.
Okay. Are there any changes to the start components supplied with your HC compressors to limit ignition and arc potential?
Yeah, most of our compressors are already using spark-proof components, but with HC refrigerants, you 100% have to be using spark-proof components, and that actually also applies to the fan motor and the condenser and any other kind of relays or electrical components that could create a spark in the system outside of the refrigeration portion, if they have a risk of coming in contact with the hydrocarbon itself.
Okay, this one, it might not make sense to me, but it will to you. What are the charge limits testing R290 if you are not going to market yet?
I think I understand the question is if you are testing your equipment, do you have to be under 150 grams? No, if you're in a controlled environment where there's limited movement of people, and you're in a facility that can remove the gas, basically, if you're in an environment that's set up to handle hydrocarbons, um, you shouldn't have to worry about the 150 gram charge. There's really no, I don't know that there's actually anything published about running a system larger than 150 grams in your labs. But sometimes, in order to find your charge balance, you have to run the system, and you could get over 150 grams. These rules are more applied to when the equipment leaves the OEM and is put into the field.
Okay, someone asked if there's any comments on using R441A in an R290 compressor.
441A is a blend of multiple different hydrocarbons in a proprietary blend too. So the mix of these different hydrocarbons is not publicly available. You shouldn't use any refrigerant in a compressor that is not approved by the compressor manufacturer, because the compressor would not be listed in UL, so you do not have any kind of certification. The behavior of the refrigerant in the compressor is not understood, so we would not know what the compression ratios are necessarily in the system. We wouldn't understand what the temperatures of the system would be if you end up with any kind of damage to the valves due to weird mass flow situations. And finally, the overload behavior would be unpredictable because we don't know what the locked rotor currents are for the compressor. We don't know where it's going to trip under certain pressure conditions because we just don't understand what the behaviors of the system are with the gas. And then, again, the UL compatibility test would not have been done, so we don't know if it would break down any of the plastic components inside the compressor. So you shouldn't use any refrigerant that's not approved by the manufacturer of the compressor.
Okay. Another question, do you have an opinion about R1234YF for MVP application? Does Embraco see any future for that?
That's a great question, but it's not relevant to the topic. So if I could have the contact information for that, I would love to follow up with the person outside of this conversation.
No problem. I will get that to you after the webinar. Let's see. Oh, here's a good one. Can standard recovery units safely be used to remove hydrocarbon refrigerants from a system?
That's a great question, actually. You can use to recover the refrigerant from a hydrocarbon system, you need to use a system that is approved for hydrocarbons because of that spark potential. So that recovery system needs to have all the safeties associated with recovering hydrocarbons, such as all the spark-proof components in it. You can use a vacuum pump, just pump down the system, and you are allowed to vent hydrocarbons in a safe environment. Basically, if you just take it out and vent it outside the store for the location that it's at, you are free to do that.
Okay. I'm still looking through. Again, if anybody has questions who's just signing on or still on, feel free to ask them in the question section on the right-hand side of your screen. What are the cost of these refrigerants? That kind of varies, I assume.
Yeah, it does vary. We expect R290 and R600 to end up being significantly cheaper than the current refrigerants. Right now, due to the fact that they're just not as common as R404A and R134A, at least in the type of quality that is required for refrigerant grade R290 and R600, There are a little more expensive, and it's going to vary by market and how you're sourcing it and the volume you source it. But right now it is a little bit more expensive, but it should drop to a much lower price as the usage increases.
Okay, and another one, are there any portable charging scales and systems, hold on, that are approved for HC refrigerants?
Yes, they are. I don't know the exact brands and model numbers that are out, but if you do a search on the internet, you can find them.
Okay, I think it's a good question, but you're the expert. So can we use our current vacuum pump, or do we need a different one? And what about the manometers? Can they be used, can HFC manometers be used with HC refrigerants?
You'll need to double check with the manufacturer of the vacuum pump if it's able to be used with R290. And as far as the manometers, I'm not actually sure. So that's something I want to follow up with later. I'll have to look into that.
Okay. Just bear with me as I'm going through some of these. Some of these folks, I see you're asking some questions I'm more comfortable giving answers to after the webinar. So I am receiving them, but some of them I will provide to John after the fact. I just want to make sure everyone who is asking question knows that. I'm not sure. Correct me, John, if you answered this one already. Somebody said we touched on cap tube sizing when going from 404A to R290, reduced by 5 to 15%. Would this be true also when going from 134A to R290?
It's a good starting point. Typically what I say is just use the cap tube you've got to start with and see what the behavior is and adjust from there.
Okay. And I think you did answer this, but I'm going to ask it one more time because we're running out of some questions. In the testing that Embraco has performed to date on HC refrigerants, what is the efficiency difference for R600 and R290 as compared to R134A and equivalent systems?
Yeah, we only touched on R290 versus 134A and 404A. So just to repeat those real quick, R290 versus 404A, 290 should be about a 15% improvement. 134A to R290, you should see 20 to 30%. R600 is actually a more efficient gas than R290. So those numbers would go up a few percent from R290 to R600. The challenge with R600 is because it is a lower pressure gas, it means you have to have more displacement to get the same capacity out of R290. So as you get to larger size compressors, the size of the compressor for R600 would get significantly larger than R290 and not be as cost effective as an R290 compressor would be. So around 800 BTUs and below, it might make sense to look at R600 if you have most of your applications in that range. If most of your applications are above 800, it may make more sense to focus in on using R290 for the smaller sizes. And at the very small sizes, 500 BTUs and below, it really does make more sense to use R600 because it gets difficult to make a good R290 compressor in that size.
Okay. Another good one. Are there any safety concerns for brazing systems with R290 with a leak that needs repair?
Well, you need to make sure to evacuate the refrigerant from the system. You definitely do not want to braze it if there's refrigerant in the system. So you pull the vacuum and be sure to purge it with nitrogen and then fix the leak and then recharge the system.
Okay. Can these gases be used on a system with a receiver?
Yes. The challenge with the receiver, you're typically going to use a receiver with a TXV. The receiver's fine. The only challenge is it does add refrigerant charge to the system because it stores liquid refrigerant. So you want to use a very small receiver, or if possible, try and avoid using it, or just use a a fat tube or something like that to store excess liquid. Because with 150 grams, it doesn't leave you a whole lot to play with for liquid refrigerant storage.
Okay. John, did you want to provide your email address for follow-up, or would you prefer to handle those one-on-one?
Yeah, no, I can provide it. It's john.prall, that's john.prall at embraco.com.
Okay, not technical, but I thought it was relevant. Does R290 have the rotten egg smell of typical propane?
No, actually, R290 will be completely odorless. The smell that you get from, say, grill-type propane is an additive, and those additives would actually damage the compressor. And this is part of the reason why you can't use the propane that you buy at Home Depot in the system. A, because of the moisture content being too high, and B, these additives would damage the compressor itself.
Okay. Just give me one sec as I am scrolling through. I'm hearing a lot about R32 being used for air conditioning. Is that a hydrocarbon? Can it be used for medium temp refrigeration?
Actually, R32 is the base for a lot of the HFOs. It is not a hydrocarbon, but it is a flammable. So it's being used in the basis of a lot of these, what you're hearing called A2Ls. These are refrigerants that are being tested, but they're not approved for use right now.
Okay. Another question just came in. With that said, regarding the rotten egg smell, what are good options for detecting propane leaks in a store? Mercaptan odorant is not an option.
You can put leak detectors in that are designed to detect hydrocarbon refrigerants. That's really the only way you would detect them. But again, that's part of the reason why this charge limit is set to 150 grams per circuit, because if you do get a leak, the volume of refrigerant is so small, it wouldn't be hazardous as it dissipates in the store.
Okay, another question. Will the natural refrigerants require different desiccant in the dryer than what is required in 134A or 404A?
No, they should be using the same desiccant.
Okay. I'm not familiar with these terms, but maybe you can help me, John. It says, how do you see CARE 3040 as a solution for MBP application?
Can you repeat, did you say CARE 40?
30/40, CARE, I'm assuming it's an acronym.
I'm not familiar with that, so we'll need to table that one.
Okay, no
and have
problem.
it written down.
Another one just popped in. How much capacity is lost by retrofitting to these gases?
With 134A, you would, well, it doesn't quite work out that you would see a capacity change. the compressors, the way we rate the compressors is if you were, say for example, you have an NEK 2150 GK compressor, that compressor is say a half horsepower compressor using R404a. When we make the propane version of it, we actually increase the displacement of the compressor so that it would have the same capacity as the R404a compressor. And then conversely, for the 134A to propane, we would decrease the displacement of the compressor to match the capacity. So we adjust the displacement of the compressor to match the legacy compressor's capacity.
Okay. How is the superheat and subcooling value affected once the system is under load condition versus no load condition?
Under a no load condition is when, well, basically would be we have to look at a no load condition as probably a stabilized run more than a no load condition. But no load or a stabilized run condition, you have your constant. You should have basically constant superheat and constant subcooling. Under a pull down situation or a reload situation, you should expect to see a higher superheat coming out of the system because you have more heat that you're trying to remove. Subcooling should not be impacted unless your condensing pressure is changing. So again, that varies on your ambience. But superheat will definitely swing as your load condition varies.
Okay, somebody wants clarification on the difference between R600 and R600a.
R600a is isobutane. R600, I believe, is just butane itself. R600a is the approved refrigerant. R600 is not going to be a commonly used refrigerant. So I should be clarifying when I say R600a, because yeah, R600 is butane.
All right, give me a moment as I'm reading this. Okay, I'm going to read it as it is. Maybe you can help me translate a little bit. How sensitive is R290 systems for refrigerant charge amount? Even if it is less than 150 grams, R744 is extremely sensitive to charge amount, as we know. Does that make sense to you?
Can you repeat the question?
Yeah.
There might be a typo in there.
How sensitive are R290 systems for refrigerant charge amount?
Okay, yeah, I got it now.
Okay.
They are going to be, with only 150 grams, if you do lose some refrigerant, the system will be a little more reactive compared to a system that has more charge. And unfortunately, that's just the nature of a low charge system.
Okay, about how much liquid R290 is in a foot of a 1/4 inch liquid line? Does that make sense?
Yeah, no, I understand the question. Okay. I don't know off the top of my head.
Okay.
That's something that has to be calculated based upon the density of the liquid at a given condition and the volume of the tubing based upon the wall thickness of the tube.
Okay. Let's see, I think we're coming to the end of the questions. And just to repeat myself, I will John or myself will respond to any questions after the webinar if I have not responded to them on this live session. Here's one more, John. How does the mass flow of R290 compare with 134 and 404?
It'll fall roughly in between them. It's a higher density gas than R134a, but at the same time it has a higher volumetric efficiency. And then 404a is even a higher pressure gas, but a little bit more volumetric efficiency itself. So you would see the mass flow, typically you would expect the mass flow to drop from 404a going to 290.
Okay, and I think we have time for maybe one more. Are the blends of the refrigerant, hold on, ooh, sorry, okay, more are coming in, so I'm losing my place, I apologize. Are the blends of the refrigerant limited to an amount for adding gas? Does that make sense to you?
I don't understand. Are the blends of the refrigerant limited
to an amount for adding gas?
I don't understand the question. I'm sorry.
That's okay. I will follow up with that individual after to get a clarification.
Okay.
Let's see. So I'm going to ask one more because we didn't do that one. Has Embraco performed any comparisons on the TEWP of R290 versus 134A and R744?
Definitely against R134A, and we see a significant drop in going from 134A to R290, and that's TEW is the total effective warming potential of the system, and that includes the energy consumption increase or energy consumption of the system throughout a life, typically 10 years, and the global warming potential of the gas being used in the system. So you combine that together, and you account for how much the system should leak throughout its life, along with how much of the gas you're able to recover at the end of the system's life. So with the GWP in the single digits for R290, it gives it a good advantage there on the recovery and on the refrigerant leaks aspect. CO2 is also very good because it's only got a 1 GWP, whereas R134A is right around 1500 GWP. So that means every pound of 134A is 1,400 times the heating capacity in the air as CO2 would have. Now, the advantage to propane is it's more energy efficient than both systems. So I know for sure that the GWP of a 134A system will be significantly higher than R290. It's going to be in the magnitudes of 50 to 80% higher than 290. And then CO2 should have well, if it's operating transcritical, it most definitely will have a higher GWP than a R290 system. However, if it's operating subcritical, which really can only happen under very specific circumstances, it would have a lower GWP than R290, or lower TUE than R290. That's a great question.
Okay, and of course, as we're about to end and wrap up, we're getting more questions, but I just want to reassure everybody we will get all of your questions to John so he can address it after the webinar. John, I'm going to take over the screen now.
All right.
All right. I just want to thank everyone for attending this webinar, and thanks, John, for taking the time to present the topic, and of course to Embraco for sponsoring this webinar. For those of you who would like to view this presentation at a later date, you can do so in the next few days on the members only section of rses.org, which I will show you how to get to right now. First, you go to rses.org and then you log in with your username and password. Underneath your name here is the My RSES homepage link that you're going to click, and then select the webinars on the left-hand side of your screen. Here are upcoming webinars, and then right below them are the archive sessions. So obviously this one will be moved to archived in the next couple days. If you have any questions, you can email me at webinars@rses.org. Again, that's webinars@rses.org. Thanks again, everybody, for attending. I hope you all have a great night. This webinar is now concluded.